Okay, calculus cowboys and cowgirls, cow people. Anyway, this is assignment 22, higher derivatives and concavity. We have a function here. We're going to determine some information about it in order to graph it. Now, you know what? Increase, decrease, max, min. I want to remind you that that would all be first derivative information, wouldn't it? So actually, this would just be this portion of the question, these boxes that I'm asking you to fill in, please. That's all f prime of x, isn't it? So the idea would be we're going to find the first derivative and do exactly what we did on assignment 21. So let's take care of that first. So f prime of x, we find the derivative. Go back and look at your notes. Doodle-doo, doodle-doo, from assignment number 20. And so that's our first derivative. And as you recall, we set it equal to 0 to find critical points. And this would be horizontal tangent lines, right? Slopes of tangent lines. Slope of 0 would mean that it's horizontal, all right? In this example, I believe this is just algebra, we could factor out 4x, and that would leave x squared minus, oh dear, what's 108 divided by 4? 27, I think, all right? Yes, all right, and then how about we set each of these equal to 0, right? We got it factored, and so 4x equals 0 leads to x equals 0, and then x squared minus 27 equals 0. Add the 27, this is just algebra, square root both sides, and you got to remember that the square root of 27 would be a plus or minus, wouldn't it? So plus or minus the square root of 27, which is a decimal approximate. You know, we need to decimalize these probably so that when we go to graph them, we'll have a general idea of where it is. So anyway, the square root of 27 is right around, let's call it 5.2-ish. All right? We'll leave it exact when we report it here, but we need to know approximately where that would be on the number line when the time comes to graph this. Because again, the entire goal of this is to graph this function. All right? And I didn't put this all up here, but increase, decrease, max, min, and that's all first derivative information. There are no division by 0 here, so we don't have to worry about undefined. So it looks like we have three critical values on our f prime of x here. And so we are going to, let me move this up here. So this is x, this is f prime of x, okay? And we have negative the square root of 27, which is about negative 5.2. We have 0, and we also have positive the square root of 27. It's about 5.2, right? Okay, so I don't know why we need to whisper, but anyway. And these are places where the first derivative is 0. This is all old stuff. This is assignment number 21, all right? But we're going to add to it here. We're going to add more information about the graph. That's what's different about this one. So this is all review. And so then we go test numbers in the derivative. For example, negative 10 would be down here below negative 5.2-ish. I need to get this out of the way. Hit pause anytime you need to. All right? So anyway, in the derivative, in the first derivative, negative 10 to the third power would be negative 1,000 times 4. That's negative 4,000. And then negative 108 times negative 10 would be positive 1,080. You don't have to do all the arithmetic once you can tell that that's going to be a negative number and negative slopes, right? So wouldn't this graph be decreasing from negative infinity to negative the square root of 27, which is about negative 5.2, all right? And you've done this. This is review. F prime of negative 1, that's in here, isn't it? Negative 1 cubed is negative 1 times 4. That'd be negative 4. And then negative 108 times negative 1 is plus 108. That's going to end up being a positive number. And remember, this tells you slopes of tangent lines. Positively sloped lines go up. So from here to here, we're increasing. So from negative the square root of 27 to 0, we're increasing, which is about negative 5.2. All right? f prime of 1, isn't that between here? That's 5.2-ish. 1 cubed is 1 times 4, that's 4, and then minus 108 times 1, and it looks like that's also going to be negative, right? Tangent lines, negatively sloped, decreasing. We've talked about this on a previous episode of calculus, all right? So from 0 to the square root of 27, decrease, and then f prime of a number beyond 5.2-ish, how about 10? All right, let's see, 10 cubed, you're welcome! 10 cubed is 1,000 times 4, that would be 4,000, minus 108 times 10 is 1,080. I can do the math on that. I can tell it's going to be a positive number. That's all that matters, right? You don't have to do all the nitty-gritty arithmetic. You just need to know positive or negative. Just remember, negatively sloped tangent lines, positively sloped. So wouldn't that interval there be an increase? So from the square root of 27 to infinity, this is it. So you can always get an idea. The graph is going to come down, go up, come down, go up. That's all first derivative stuff, all right? That's old stuff. And then we, look, when we're going to graph things, we need to plot points. That's what these maxes and mins would represent. And it looks to me like negative the square root, come on, when we're going to make it into an ordered pair, let's call it negative 5.2-ish. All right, this is going to be approximate. And what we're beginning to talk about is finding these ordered pairs. So we put them in the function, don't we? Now I'm going to put negative the square root of 27 in there for x. So anyway, that number, putting it into the function, that's how you find points, right? These are going to be ordered pairs. So the square root of 27, all right, let's see. So that number raised to the 4th power minus 54 times that number squared plus 237 gives us the ordered pair negative 492. All right, now look at the profile of this, decrease, increase. This is assignment 21 all over again. So wouldn't that be a minimum point? And so let's put that in that minimum box, negative 5.2-ish, negative 492. All right, 0 plugged into that function. In the function, 0 to the 4th, 0 squared, 237. All right, what's that? Max, graph increase in, decrease out. That's a max. The ordered pair 0, 237. Hopefully everybody's like, this is assignment 21. Oh my gosh. All right, and then the square root of 27. And again, we're putting these into the function. That's how you get ordered pairs. So you put the square root of 27 here, and so on. And again, that's approximately 5.2. And that turns out to be negative 492. And what do you think? Minimum. All right, so thus far, you're all thinking, when are we going to learn anything new? This is old stuff. This was assignment 21. Increase, decrease, max, min. First derivative test. All right, that's what that was all about. So we're done with that. That's our first derivative test and everything. Okay. Feel free to hit pause anytime. That was all F prime. Okay, what are these concepts? Concavity. Concave up, concave down, inflection points. That's what's new. If you've been napping, wake up! This is new. All right? So here's the deal. The way we analyze concavity is we do the exact same analysis on the second derivative. So in the notes that were sent to you, let's talk about determining what are called possible inflection points. Second derivative, the derivative of the first derivative. Do it again, it was so much fun. So this would be what? 12x squared minus 108. And you know what we do with that derivative? We set it equal to 0, and we check for undefined. Sound familiar? I hope so. It's the very same analysis that we perform on the first derivative. All right, so the point is, all of this down here, concavity and inflection, is going to be f double prime of x, the second derivative. And when we're done, we'll try to understand what this is telling us. It doesn't have to do with slopes of tangent lines. It's something else. But anyway, when we set this equal to 0, just do some algebra. Let's see, add over the 108, divide by 12. Let's see, what's 108 divided by 12? 9. And then the square root would be plus minus 3, wouldn't it? Nice round numbers. Okay, so plus and minus 3. Those are possible inflection values. All right, undefined. I could give you questions that do more of that. We're trying to keep it simple. But anyway, there's no fractions here, so we don't have to worry about division by 0. So, you know what? We're going to do the very same sort of analysis here on x f double prime of x, whereby we put -3 and 3 on here. It's a different number line, isn't it? And it gives us different information. Okay? So, we do the exact same sort of things we were doing earlier. We will break the number line up into 3 regions this time. And we are going to do the second derivative test. We'll go f double prime of, let's say, -10. We're putting it in the second derivative, right? That's why it said f double prime of. So -10 squared is 100 times 12. That's 1200 minus 108. That's going to be a positive number, isn't it? Okay? That's going to be a positive number. Okay, so we're going to put positives here. Incidentally, I needed to put the fact that these two numbers made the second derivative equal to 0, didn't it? What does a positive second derivative indicate? It indicates that it is what's called concave up. The second derivative is greater than 0, otherwise known as positive. F double prime of x is greater than 0. Concave up. Okay. Now the best thing I can think of is that talks about the curvature of the graph. And when something is concave up, the visual I get is a parabola that opens upward. There's upward curvature to it. It's not perfect, but that to me is a good way of trying to describe that. So instead of like a slope of a tangent line, which is what the first derivative tells you, this tells you the concavity, the curvature. And so from -infinity to -3, this thing is concave up. Okay, just straight up concave up on that one. All right, best I can do for you. When we're done graphing this, I'll do my best to pull this all together. And again, board space is at a premium, but we'll do what we can. F double prime of 0, a number in between. Second derivative, that'd be 0 minus 108, that'd be -108, otherwise known as negative. So in this interval, what? Concave down. Second derivative is less than 0. F double prime of x is less than 0. All right, concave downward, a downward curvature. All right, I don't know how else to, that's my little logo for concave down, downward curvature. Okay, so from -3 to 3, we're concave down. Very much the same analysis, it's just the interpretations are different. Instead of slopes of tangent lines, it's concavity, it's curvature, for lack of a better description. All right, f double prime of 10, 10 squared is 100 times 12. Second derivative, right? So that'd be 1200 minus 108. That's going to be a positive number, right? So that's plus, positive. So here we are again, we're back to being concave up. That's the general curvature. And this is hard to see on a graph sometimes. It's not as easily visual as maxes and mins and things of that nature. So there we go with that. So what is an inflection point? Well, first of all, it's got to actually create a point. So just like we talked about, these are what I would call potential inflection points. And they have to pass two things, in my opinion, for that to be an inflection point. The first would be that it actually creates a point, first of all, ordered pair. Now, if we have a value of x and we want to see if it creates an ordered pair in a function, what do we put it into to find that ordered pair? Yes, the function. That's right. So we would put that -3 into the function here, right? That's how you get ordered pairs. So, anyway, let's see. -3 to the 4th power minus 54 times -3 squared plus 237, plugging it in the function, -168. Okay, so that would be an ordered pair. Now, it works in the function, that's the first thing. What else? The concavity has to change at that number. And you'll notice here that the concavity changes from upward positive to downward negative. Is that an inflection point? Yes, the concavity changed. All right, now you could have plus plus. If that were the case, plus plus, that would not be an inflection point. It would be a point on the curve. It just wouldn't be considered an inflection point. All right, so that's an important thing to note here. So, given the fact that the concavity changed, that is indeed an inflection point. Okay, then we go put 3 in there. Now look, this is somewhat coincidence, but 3 in the function gives the same number here. That does not always have to happen. Put it in the function, okay, crunch the numbers. Is that an inflection point? Yes, concavity changed. So that is also going to be listed as an inflection point. 3, -168. So, again, I'll say that information there is pretty much the same. It's obtained in the very same fashion as the first derivative. It's just that the information obviously is different. Instead of slopes of tangent lines, it has to do with concavity, the curvature. Okay? So now it's a matter of putting that all together to create a beautiful, wonderful, awesome graph. And so now I'm going to take some time here to put some graph paper. And I'd love to leave these up here. I guess I'm going to try to squeeze this in. I don't know, this might blow up on my face, but oh well. Wish me well. I'm nervous trying to squeeze this in over here, but I think we can handle this. And okay, let's start talking about scale. You know, if you look at the x numbers, the values of x that we've determined so far, and this is where I would probably look at these ordered pairs that we're about to plot. But you'll notice the values of x are -5-ish, 0, 3, -3. I think scaling the x-axis by 1s seems reasonable. And so we'll have 0, 1, 2, 3, 4, 5, 1, -1, +1, 2, 3, 4, 5. Okay, get the idea? Scale by 1. If you look at the y's, that's about 500, that's about 150. I don't know, I would be of the opinion that the y-axis, the scale on the y-axis, might be more conducive to 100ths. What do you think? Think so? It's arbitrary, okay. So use whatever scale you want for each axis. But I would wait until I find these numbers before I start getting all crazy scaling things. All right, so let's start with the easy stuff first. Let's plot these max-min like we did on the previous assignment, number 21. So, right here, let's see. -5, 0, 237. Okay, we'll go with that. So 0 on the x, 100, 200, 300, 0, 237, right about in there. Good enough, get me close, all right? And then we've got this ordered pair, -5.2-ish, that was negative the square root of 27, -492, well, let's see, here's -5, and then remember, we're scaling by hundreds, so 100, 200, 300, 400, 500, so -5.2-ish, -492-ish, get me in the ballpark, I'll be good, all right? And then we've got this point, 5.2, -492, so that would be just a slight 1, 2, 3, 4, 5. It'd be a little bit past 5. And then remember, we're going by hundreds here, so that would mimic the other one over there. 5 comma negative 492. Now look, we could graph the thing. And we will. And that would be good enough information to get a pretty rough graph. But why don't we make the graph a little bit better by putting these inflection points in here. The more points you can plot on a graph, the better that graph will be, in my opinion. Okay? And so, -3, -168. -100, -200, okay, -3, and then +3, -168 on the y-axis. There's more points. So, all right, let's put it all together and make a graph. I'm not an art critic, I'll do my best. So it decreases to here, right, decreases. And between here and here it increases. Now, keep in mind that as it does so, it hits that inflection point and then continues on, okay? Then it hits this point, then it goes through this inflection on down and hits this one, and then increases back up, right? Down, up, down, up. There you go, that's our rough graph of this thing. Very rough, it's fine. These inflection points are very difficult to get a visual of or an understanding, but you don't need to put this on your answer, but see, this curvature was upward mostly, and then at that point, which in my opinion is quite imperceptible, but the tide began to turn the other direction, and between -3 and 3 on that x-axis, it was more curved downward, all right? And then, once it hit this point, it began to curve back up again. So that's my best attempt at explaining concavity as to that somewhat imperceptible point where the tide began to turn in the other direction on those curves. And so, you know, the rate of increase or decrease. Anyway, I don't know. It's hard to explain it. I'm struggling. I need to go eat lunch. But that's what we're looking for on this. I think we'll maybe do 2 more of these, just so you know. We're going to do examples 2, and I think maybe number 5. So, anyway, take a break. We'll come back, we'll do example 2. Let's go stop the video first. Okay. Yippee-ki-yay!